Okay. All right. Are people seeing my slide here?
Yes, we can. Thank you very much.
Excellent. Okay. Well, thank you again for inviting me to participate in this seminar series, and hello to everybody, whatever time of day it is for you. Um, I want to talk to you today about the future of seeing. You may be expecting me to dig into the operations of MRI machines or other medical imaging devices, given the background that you just heard. But after more than a quarter of a century of doing that, I found myself more and more interested in stepping back a little to consider the origins and the evolution of what we do as imagers. I actually have a book called The Future of Seeing coming out sometime next year. And I thought I would, for a change, give you a preview of some of the themes I explore in that book. Um, I'd like to review with you briefly the rich history of the human quest to see what was once invisible, because that is, after all, what we do as imagers. And then I want to consider with you what the future of imaging might look like so that you can consider how you might experience that future and also how you might shape it. And so, in particular, I want to explore, as you see from the subtitle here, how imaging will return to its deep origins and will one day belong to everybody again. So, what do I mean by imaging belong to everyone? Well, in one sense, it already does. We're all creatures of imaging because imaging is seeing, and seeing is imaging. So, as I look at my screen today, I see you, and of course, you also see me. Imaging is baked into our biology in the form of our eyes and our other senses. And it's also baked into our language. Often we say seeing in the sense of understanding. And then, of course, increasingly, it's incorporated as well into the tools of daily life. So I actually love the title of your seminar series, Camera. Camera, of course, was once a highly specialized tool developed by, if you will, some imaging researchers. But of course, now cameras are in pockets everywhere. There are actually more cell phone cameras than there are people on Earth. And this remarkable development kind of reflects a general trend towards miniaturization and broad dissemination of imaging technology. But there is another opposing trend in imaging as well, not just a push towards omnipresence, but a kind of specialization and refinement. And over time, many kinds of imaging have become the domain of specialized experts. So take telescopes, for example. You see the twin Keck telescopes in California up top, the results of imaging with the Event Horizon Telescope, a sort of Earth-wide telescope um, that showed us our first views of black holes are shown in the middle. And then, of course, we have MRI machines. And most people don't see themselves in these devices anymore. Some of you in the audience may, of course, be exceptions to that. So basically, um, I'd like to spend a little time today exploring how things got that way and how things are poised to change. Hence my outline for today. First, a lightning tour of the history of imaging, and then I want to consider together the future of imaging. I know your camera seminars are configured, at least sometimes, as case studies. So without breaking the mold too much, I suppose I'd like to consider all of imaging today as a case study. So let's start by looking back at the deep history of imaging. The first imaging technology was actually not one we invented. Biology did that for us. So in the early oceans, the ability to tell here from there conferred a powerful evolutionary advantage. And so in the Cambrian era, about 500 million BC, there was a veritable arms race to develop eyes, culminating in some pretty advanced eyes like this trilobite compound eye shown here. The trilobite is that creature you saw on my title slide. And they had these multifaceted compound eyes pretty remarkably early in evolution. From that point, it was really just a hop, skip, and a jump to our human camera eyes, which bent light and focused it and had many other remarkable capabilities. And of course, our eyes are not even close to the most powerful eyes out there in the world. Nature's continued to innovate, creating this remarkable diversity of animal eyes. So after we had eyes and brains, it took us a while and a whole lot of trial and error to emulate nature and improve on it. And the next big leap occurred, I maintain, when we figured out how to bend light. Our own eyes, of course, were doing this with lenses inside, but we didn't know that then. Basically, someone picked up a piece of sea glass at some point in early prehistory and looked through it and saw strange distortions. Those distortions arise from the fact that a lens bends light. It takes straight lines and bends them down to a focal point, as you see here, or it takes diverging lines from a single point and refocuses them back to another copy of that point, generating, as a result, an image. So people figured out after a while, starting around 1600 AD, that if you took two of these lenses and you put one at the point where the image of the other one was formed, you could actually magnify those images pretty dramatically. And that led to the telescope, which you see here, with its two lenses, the objective lens and the eyepiece lens. And that led to the microscope, which had a similar arrangement. And instead of seeing far things as if they were close, it could see small things as if they were large. And ultimately, this type of bending of light gave us the gift of magnification, which really gave us access now to the cosmos and also to the microcosmos. And it also gave us our first imaging tubes. And what I'm showing you here are, on the left, Galileo's first telescope, developed a little after 1600 AD, and then a line drawing on the right of one of the early microscopes from Hooke's famous treatise, Robert Hooke's famous treatise, Micrographia, which basically showed people all kinds of sort of miraculous microscopic things that they never knew existed. And then, of course, bending light and magnifying was one thing, but it was kind of a royal pain if you couldn't actually then record that image and share it with others. You had to have your eye sort of right up against the eyepiece to see these things. Well, in around the 1830s, some enterprising inventors figured out how to actually use chemical film to store these images. And so you see on the left here a picture of a daguerreotype by Louis Daguerre, who's shown in a daguerreotype image on the right. He invented, or some would say co-invented, there's a whole fun story about that, a way of now capturing images archivally. And in fact, he had a pretty fun thing to say after this was done. His quote was, "I have seized the light, I have arrested its flight." So for the first time now, light could not just be bent and magnified, but it could be recorded. But that leads to the next innovation that I think was key. Basically, if we wanted to now see beyond the surface of things, we needed to get through barriers like the skin. And in 1895, Wilhelm Conrad Röntgen discovered the tool we needed in the form of X-rays, essentially light on steroids, which could blast its way through previously opaque things and then be recorded on similar photographic film. And along with X-rays, I maintain, came a new transform, basically one step more advanced than simple bending. X-rays, which were hard to bend, could actually travel through objects and could be attenuated differentially by structures of differing density, and you see that here. And the resulting, images, what was left on the other end was actually basically a sum of the densities of structures in all the cross sections of the body along the path of the X-rays. So basically, you got a smushing together of all of those structures into what we call a projection. The resulting shadow pictures or projections are really what created the field of Röntgenology, which evolved into modern radiology. Okay, well, that's fine, but if you smush an object together, you can get some sense of what's inside, say side to side, but you can't really tell where it is front to back. So the next trick was to sort out all the different cross sections buried in that sum I showed you before. So if I go back, you have this sum here, the next thing was to figure out what each of those cross sections were. And it turns out the magic trick there was to take multiple different projections from different angles and sort out what must have produced all those different projections. That trick was called tomography, and it generated another set of now familiar imaging tubes for CT, PET, and MRI. And sort of interestingly, all of those modalities really got their start in around the 1970s, in part because that's when computers were just being developed and could do this sort of mathematical sorting out efficiently. Okay, well, as the 20th century progressed and gave way to the 21st century, we imagers learned how to pack diverse information into our voxels. So we developed all these diverse tools which allowed us to see the same thing basically in many complementary ways. So I'm showing you that here with two different types of images. On top, you see various different views of the Crab Nebula, a nebula out there in the universe that actually contains this pretty remarkable supernova remnant about the size of New York City that's spinning 30 times a second. So imagine the energies involved in something the size of New York City spinning 30 times a second. It generates all kinds of emissions across the electromagnetic spectrum, and you see telescopes that have been developed to capture each of those different areas of the spectrum. So you have radio wave, infrared, visible light, ultraviolet, X-rays, gamma rays, and they all show you different aspects of that same nebula. On the bottom, of course, you see a bunch of different MR scans in an MR protocol, and these were actually taken from a report of, I think, one human subject who was imaged some crazy number of times over the course of his life for research. And as you can see, we can view many different types of things, from water content, fluid made bright or dark, blood content. We can look at diffusion and look at nerve tracts. We can do functional MRI and observe the brain, in action or at rest. Well, what did we need in order to get some of those many different types of images? Basically, we needed, in the case of astronomy, certainly, more and more advanced, and in most cases, larger and larger imaging devices. So in astronomy, bigger was often better if you wanted to push the limits of spatial resolution, signal-to-noise ratio. We started out with just sort of the small tube on the left, but then we got these huge telescope dishes. And I mentioned before the Event Horizon Telescope. What that does is it takes dishes spaced really around the globe and forms a telescope of the effective size, by some accounts, of all of Earth itself. And that's what gave us, again, those views of black holes. Well, so how about in medical imaging? Well, in medical imaging, we had sort of a similar trend. And let's just take the example of MRI. Back when MRI started in the 70s, the field strengths were on the order of 0.1 Tesla. But as time went on, we grew to stronger and stronger magnetic fields, basically to give us more signal-to-noise ratio. And I'm showing at top a sort of 2000 era, 2000 vintage 7 Tesla scanner. That happens to be the 7 Tesla MRI machine we still have at NYU. And you would think, the progress would keep continuing, and in some ways it has. There's now a 10.5 Tesla scanner and 14 Tesla scanners. But actually, as I'm sure many of you know, in recent times, there's been another trend in precisely the opposite direction. So in contrast to the historical march to progressively higher field strengths, in recent times, we've seen this, new efflorescence of startups, as well as big vendor offerings and research projects involving inexpensive, accessible, low field scanners. And so down at the bottom there on the right, you see a 64 millitesla hyperfine swoop scanner that we also now have at my institution. And of course, the hyperfine scanner has been one linchpin of a real push towards accessible MRI. And I don't know how many of you have seen or for that matter, been involved with the ISMRM's new push, the International Society for Magnetic Resonance in Medicine, its new push for accessible MRI. The argument being that 2/3 of the world's population has no access to MRI. And so ISMRM is partnering with the Gates Foundation to try to get scanners to various places in Africa and eventually, one hopes around the world that do not currently have access. I see this as a very important beginning and a very exciting approach to making imaging accessible. There are a lot of issues that need to be confronted with, say, image quality, which suffers as you go down in field strength. But for the rest of at least this segment of the seminar, I wanted to talk not just about the familiar question of getting imaging to places that don't have it, because there are actually other gaps as well. There are gaps in time. And if you think of how we use imaging nowadays and have for decades, basically it's used in this episodic manner, right? So you have some symptoms, you have something that brings you to a physician, and then you're sent off to get an image, whether in a hospital or an outpatient setting or wherever these relatively scarce imaging devices are located. But in between those times, there are these huge gaps when we're not imaging. We see nothing. These are sort of gaps of invisibility. But interestingly enough, healthcare is moving in a different direction than that. And this is a slide I borrowed from a colleague of mine, Dr. Devin Mann, who characterizes the 3,000 plus year evolution in healthcare from sort of the pre-modern era when basically doctors visited people in their homes to the modern era of episodic care, where basically you have people getting sick at home, but then having to travel to the doctors in ambulatory or hospital facilities. But he argues, and many people agree, that in the future, it's going to be a model of continuous care where people are enabled once again where they live, backed up by episodic care in ambulatory or hospital facilities. And that's a really interesting and exciting picture of the future of healthcare. But the question it always raises for me is, what's the role of imaging in that? Imaging, is currently in those big devices that sit in ambulatory and hospital facilities. So is imaging basically just going to be a backup player in this future of continuous care? We just come in when someone else has caught the disease, maybe even characterized it, and we just take a picture of it for good measure? Or can we actually think about moving imaging up to the front line? And so basically now, when I consider with you for the next little while the future of imaging, there are a few questions that sort of occur to me from thinking about this history of imaging that we've just explored together. First of all, we started this whole imaging phenomenon in biology. So what lessons can we actually learn from biology to do imaging better? How will we, learning from those lessons, build the imaging devices of the future? And how can we fill gaps both in space and in time so that we can truly bring imaging to everyone everywhere? So I'll spend a little bit of time on that, and then I'll pause, and we'll see where you all want to go from there. So I have two principal lessons from biology that I want to talk about. Both of them derive from how natural biological vision works. The first I call emulating the senses. The second I call emulating the brain. So here's lesson number one. So you're looking at me, right, as I'm giving this presentation, and I probably look like, okay, I'm moving my hands, I'm moving my mouth, but otherwise the scene is relatively static. But that's actually a little bit of an illusion because it turns out your eyes, as you're looking at me, are always moving. So we see what looks like relatively fixed scenes with things moving through them, but actually our eyes are constantly jittering. They're undergoing these sharp jumps called saccades. They're slowly drifting back and forth, and you can just see some examples of this type of eye motion tracked on this slide here. This is a slide from Michele Rucci, who's a neuroscientist at University of Rochester, who has studied the effect of eyes moving like this. And you would think that if the eyes are constantly jittering, well, maybe the scene would be jittering too. Why not? And in fact, the classical view in neuroscience was that these involuntary, uncontrolled movements were messing up imaging, and somehow the brain was overcoming all that motion. But actually, interestingly, recently, neuroscience has come to a different emerging view, which is that actually these movements, these saccades, these drifts, are finely controlled, and they're actually part of image encoding strategies. How can that be? How can it be that if you move your eyes, you get a clearer picture? Well, so one way Dr. Rucci explains it is that we sort of see space through time. So you can imagine if you have an image with some contrast, say these striped images here, if you just stare at them with fixed eyes, okay, you have spatial contrast that you can look at, but there's no change over time. It turns out, though, that our brains are exquisitely tuned to changes in time. So in fact, if you move your eyes back and forth across these stripes, then you can actually get a signal which varies not just as a function of space, but as a function of time. And it turns out that it's now believed that's one way that the eyes and the brain use motion to actually give you better visual acuity. And people have done the experiment. They've sort of set up a computer so that as your eyes move, it tracks your eye motion and it moves the image with the eyes so that relatively speaking, they're static. And people have a harder time seeing when that happens. Okay, well, so I've just spent all this time on how the eyes are constantly moving. That begs the question, why are our medical devices so rigid, right? We have these big, expensive, carefully calibrated tubes. And then what do we do when someone comes into those tubes? We tell them, sit still, don't move, freeze, which of course is not a particularly natural type of thing. And why do we do that? Well, because, say, in MRI, what we're doing is we're gathering these orderly ranks of projections. And we want those projections to be nicely ordered so we can convert them into a well-defined image. But there are alternatives to this type of approach that are emerging that I would say are starting now more to emulate the way vision or the way the senses do it. And I love this little quote from Paul Simon, staccato signals of constant information. Basically, if you think about it, that's what the senses are doing. As you're sitting listening to me, you're getting a stream of sensation visually, but also auditory sensation and tactile sensation and everything else from your environment. So basically, it's not a model of snapshots like we're used to in medical imaging. It's a model of streaming. There's an approach that we've been working on at NYU for many years and a number of related approaches out in the field now that use instead a kind of continuous acquisition, not an orderly rank of linear projections, but in this case, a set of radial projections that are acquired continuously with each radial projection filling in the largest gap in angular space from before. And it turns out if you gather in this kind of continuous way, you can then reconstruct images very flexibly because each spoke essentially works equally well with all others. So you can group a large number of spokes together and get a nice high resolution image that's kind of slow, 17 seconds per frame, or you can group a very small number of lines together, use some advanced techniques to reconstruct them, and get, say, 1.5 seconds per frame. So you have that flexibility, and you can use this type of approach in all sorts of different body areas. And importantly, this means your patient can also be moving while you do this, but you have a constantly refreshed view, and so you can correct a lot of that motion. So that's a technique called the grasp technique, but there are a lot of other techniques out there that use sort of continuous acquisition approaches. One that people may have seen if you happen to be in the MR field is something called MR fingerprinting, which instead of having, again, this nice orderly rank of projections, creates what seems like sort of a crazy disordered set of, of data acquisitions and converts that into a quantitative map of tissue parameters. But there's another way we could emulate the senses, if you think about it, right? We don't just have our central nervous system, our brain, we actually have a whole diverse array of peripheral nerves, which bring us all kinds of other different signals, not just our two eyes vision, for example. That type of approach is already being taken in other types of technology, like self-driving cars, which have all of these different sensors integrated in them, and they're constantly probing the environment around and integrating that to kind of ideally keep you safe. You can think of doing the same thing with, say, MR scanners or other types of medical imaging devices. So this is an example of work we did at NYU, just trying to incorporate a bunch of different types of sensors into the MRI machine and measure with them while we were getting the MR images. These included something we call a pilotone, which is basically just a radio frequency device listening for changes that can tell if, say, your abdomen or your heart are moving. There are ultrasound transducers that you can just put right on the body, and they send pings out into the body, and you get these complex signatures back. There are 3D cameras that can sort of track what's happening on the outside, and various other types of things. And lots of other people out there in the field now are starting to put different types of sensors inside MR machines and other imaging devices. This is just one example from a colleague, Mickey Lustig. He calls it MR dust. So basically, little sensors connected wirelessly that can get you all kinds of ancillary information. Okay, so then let me go to lesson number 2. And this involves what I call the myth of depth perception. Remember I said before that these kind of static images that you see when you're looking at something are a little bit of a fiction because your eyes are constantly moving. Well, it turns out that the way depth perception is usually described is also kind of a myth or an illusion. So the way people usually describe how we can see depth is that, okay, well, we've got two eyes. So when we're looking at something, the eyes are pointing differently. We get different views. We kind of triangulate and we work out from that how far away something is from us, right? Wrong. That's, I won't say a complete lie, but at least very much a partial lie. And that's because if you think about it from the point of view of the type of imaging I do, tomography, two-dimensional projections is not nearly enough to represent all of 3D space. And in fact, if you close one eye and you look at a scene you've been looking at for a while, you can pretty much still tell how far something away is. So this whole idea of triangulation with binocular vision, something has to be wrong with it. You can still see some kind of depth, or at least intuit it with one eye. So what's going on? Well, I believe, and I think there's, some evidence out there in the neuroscience community that our brains are actually relying heavily on prior knowledge. For example, you generally speaking know the relative sizes of things, right? You know that if you're looking at me across a room, I'm a human, probably about a room's distance away. I'm not a giant, an entire field away. You also know subtleties of lighting and all of that. And so the brain is actually bringing in a lot of these a lot of this prior information to tell you a lot about the depth. So that then begs the question, can we do something similar in imaging? Well, there is something that people are talking about a little bit nowadays that kind of emulates the brain, and that's machine learning. And what does machine learning do? Well, machine learning is actually, if you look at it in the right way, a way of encoding prior knowledge. So I've just shown you an example here of an encoder in a so-called convolutional neural net. So classic AI structure. And what it does is it takes, say, an image, in this case, an image of this dog, and it distills it down through many different layers. The first layers, it's known, sort of pick out low-level features like edges and shading. And as you get up to higher levels, you're picking out high-level features like eyes and fur and so on. You can then train a neural net by showing it lots of different examples and modifying the connections between the different layers and the nodes within each layer. You can train it to do, say, a classification. Oh, yes, this is a dog, not a cat or a skunk. But one interesting thing that happens at the sort of narrow end of this funnel is before you make that classification, you actually have what's called a feature vector, which is a very compact representation of the key features inside that image. Well, so one thing you can do with that type of representation learning is you can take crappy images and you can rescue them. So you can take this degraded image of the Mona Lisa, for example, that I've shown you here. You send it through what's called an autoencoder. In the center is that representation, that feature vector here, and you train it to essentially wipe away the noise and maybe increase the resolution and give you the full image. You can naturally imagine the benefits that that might have if you're, say, trying to do low field MRI, which has very comparatively low SNR, but you have now these approaches that can wipe away some of the noise and get you a prettier looking image. But there's actually a lot more you can do than just cleaning up images. You can reconstruct images from limited data. So you can take a limited set of MR data, for example, which would give you a really crappy image with lots of aliasing and folding artifacts and so on. And you can reconstruct it back to full content. That's something that is now being done on many scanners around the world. More and more vendors are introducing this onto scanners. But we don't need to stick with just image quality, do we? You can also use approaches like this to get answers rather than images from limited data. So let's say you had one of these low field scanners that I'm showing you here. Rather than trying to create a pretty image, what if you just tried to answer the question, hey, does this patient have prostate cancer or a high likelihood for a high risk of prostate cancer? Yes or no? Is there a bleed in this person's brain? Yes or no? And in fact, we've done some work at NYU to try to see how low can we go. Basically, how little data do we need if we have a well-trained AI system whose job is just to say disease, yes or no, or high risk, low risk. And it turns out if you just want a binary answer, not a complete characterization of an image as you need in standard radiologic practice, then you can get away with remarkably little data. In this case, something like 20-fold less data. So you can take a 20th of the data and still get a very robust answer, high risk, low risk for prostate cancer, for example. And there have been other studies we've done with colleagues that show that the same thing applies if instead of taking less data, you get worse data. So this is just a receiver operator curve, which characterizes essentially the accuracy of this same answer. Does a patient have a high risk or a low risk of prostate cancer? And it turns out if we degrade the underlying image in signal to noise ratio, we just throw lots and lots of noise in until we can barely see the image anymore, the network still gets the right answer, high risk or low risk, down to a really remarkably low signal to noise ratio. We found the same thing if you degraded the spatial resolution of the image. So if you have a well-defined answer that you want to get, you can get by with less or with worse data. But then there's more you can do as well if you think about it. Normally, when we image someone, we don't change the way we image them if we've seen them no times before, 10 times before, or 100 times before. But we can start thinking about using the axis of time using prior information to condition what we do this time. So you could imagine, for example, if you have a list of old scans that have been obtained in a person, and now let's say you have a very limited set of new data with a lot fewer lines of data, for example, than you normally would have gathered. Well, you can use neural nets like this to use that very limited data set just to detect, has there been a worrisome change from last time? And I have a couple of students working on this type of problem right now to see how little data we can get away with and how much prior information improves your assessment of worrisome change. And for that matter, if you're taking a limited data set to assess change, do you even need that data set to be the same imaging modality? What if instead you had some of that new sensor data that I was talking about? If you're putting a bunch of sensors inside the MR scanner, if you had a bunch of old scans, could you actually detect worrisome change just off of the outputs of these sensors, which could be wearable sensors? They could be, stitched into your clothes, or they could be, wrapped around your wrist. And so this leads to kind of a new potential paradigm that I think is going to be at least one fascinating possible future for medical imaging. And I'm showing it to you here. Basically, the idea is, okay, let's say you get a traditional scan early on in, a fancy, perhaps, slightly more accessible than currently, but high performance scanner. You use artificial intelligence to get a nice representation of your health state from those images. But then maybe the next time you come in and you get scanned by a scanner that's built into a seat, a low field MRI machine that doesn't produce particularly pretty images at all, but maybe gives you just enough to assess change. And then maybe in between those types of scans, you actually walk home with wearable sensors, or you have sensors in the environment. That might then be enough to detect significant change too. And the idea here is that you can build up sort of this progression of representations of your health, but each of them conditioned on all of the prior information that you have. And if at some point there's something that says, ooh, you know what? These data I'm getting aren't consistent with your prior normal. Something's different about you today. Then you get referred to go and get a fuller scan. And this is something I've been calling the Everywhere Scanner Project. The idea is that this is at least one route to imaging for everyone, everywhere, and at many more times than we're used to in traditional practice. So a few final comments about the future of medical imaging, and then I'll pause for some questions. I think that there will be new technology, whether it be accessible scanners or abundant sensors or a combination of them, that brings imaging to people rather than people to imaging the way we do it now. There will be new transforms, mathematical transforms, that enable coordination between different scanning and sensing modalities and between different scanning and sensing sessions. And imaging, I believe, will be used for prevention, not just when we already know you're sick and we need to characterize that disease. I think imaging will not just be geographically diverse. It will increasingly be spatially and temporally omnipresent, like the cell phone cameras that have already made a pretty good play for omnipresence. I don't think it's just going to be widely scattered accessible machines doing medical imaging as it's always been done. And sometimes people who talk about low field MRI talk about just getting imaging to more places. I think that's incredibly valuable, incredibly important, and not at all the only thing we can think of. I think we can think of imaging differently, as I've tried to show you. And in a way, I see this a little bit like returning back to our deep origins, hence my subtitle. It's a little bit like the early oceans. Eyes and other sensory organs are everywhere, helping us organisms make key life and death decisions. just a quick word on shaping the future of medical imaging. Um, I'm talking about some work that, we've done in my group at NYU and that other centers are doing around the world. I will say, though, that traditional heavily resourced radiology departments and imaging research centers are actually moving quite slowly in directions like these. And you can ask why, and maybe it's just hard to see things differently once you've been doing them a certain way for years and years at a time. But I would just remark that there is an opportunity now for innovators with a different perspective to step in, to think not just how can we make traditional radiologic imaging better, which we still need to do, and make it more accessible, which we absolutely need to do, but can we also make it different? Can we also make it proactive and preventative? And then finally, I titled the whole talk, The Future of Seeing. So just a word or two about the future of seeing. It turns out, as I'm sure many of you have determined yourselves, that actually the way we see the world is starting to change. In these cell phone cameras that we have, you can take a scene and you can use something called magic eraser to remove inconvenient parts of it you don't want to see. This, of course, gets a little bit terrifying if you think about the impact on all manner of social conventions and equity and all of these things. But I think we need to be prepared for a world in which the way we see not just patients, but each other changes. And I think there are any number of new technologies that might allow us to start seeing in new ways. And at the same time, there are these advanced transforms, AI as one key example, that make it a little bit more difficult to determine whether what we're seeing is real or not. And by the way, for your interest, the two images I'm showing at the bottom right here, these were reprinted from a New York Times article a year or so back entitled, Can We Believe What We See? One of those images is an actual historic image of a kiss in Times Square, and another is an image created by a generative AI system. And if you want, just for fun, take a minute and try to determine which one, left or right, you think is real. So that's all for at least this part of the seminar. I want to acknowledge a number of people who have tolerated me or inspired me as we've talked about what the future of imaging might be. Some of the people listed here at NYU, but also and shown, by the way, on the bottom left. This is a very old photo. I need to substitute a new one soon of some of our research group there, but also my own home team, Sarah, Hannah, and Noah, who also listen to me talk a lot about the future of imaging and occasionally weigh in with something other than "Shut up, Dad." So with that, I guess let me pause. And Aduna, if there
Yeah,
are
you still have
questions.
some time to go over the case study. So if you want to take like the next 5, 6 minutes to do that, that would be fantastic. And then we take some questions coming in. Will that work?
Perfect, perfect,
Yeah.
works for me. All
Okay.
right. Well, so the case study I chose was kind of a personal one, and forgive me, it's not going to be a classic clinical case study. So if you're looking for that, you're going to have to look elsewhere. But it's actually a case study of how I came to a lot of these opinions that I just expressed to you today, and in a sense, how my own career in imaging evolved. And basically what I stumbled into um, was a career largely devoted to making more with less. So in 1996, I uh, ended up developing some of the early techniques for what's now called parallel MRI. Um, and I'll tell you just a little bit about that and ask some questions along the way. But then about 10 years later, this fascinating new development came along called compressed sensing, which enabled us to make more with even less. And then for some reason, all these things seem to be spaced by a decade or so. But starting around 2016, with our NYU team, I started working on ways of using artificial intelligence to make even more with even less. So I'll spend just a little bit on that, and then you can ask away any questions you have. Basically, this is a picture of me as a callow young imaging scientist. Boy, am I young, and boy, did I know nothing. Um, but basically, my accidental start in imaging really began with a question. Um, I was doing a month-long rotation in the lab of a cardiac imager named Warren Manning. He likes to image the heart. And I, by the way, knew just about nothing about MRI. I had studied magnetic resonance a little bit, but in my graduate work, but not MRI. And Warren told me, if I wanted to spend the month productively, I could look back at some of the literature and figure out what it is that I wanted to focus on that month. And as I looked back over the literature, because I didn't know any better, I found myself asking the question over and over again, why can't we image faster? Because this was, of course, imaging the heart, and the heart moves, and it's considered bad form to stop the heart as you're imaging it. So speed was really of the essence. And so let me actually, and I don't know whether, you may not have the technology set up to do this formally, but for anyone who's interested, I'll ask you a couple of questions and you can choose your favorite answers.
Oh,
So
they could type it in chat too.
perfect, perfect.
Yeah.
So what limits the speed of MR scans? So you got 5 options here: gradient performance, RF pulse duration, signal to noise ratio, number of data points collected at once, or all of the above. So I'll give you a second to choose your answer if you want to. Okay. Am I clear to move on?
Yes, D's and E's coming in.
D's and E's coming in. Excellent. Well, like many questions configured this way, the answer is all of the above. If you have better gradient performance, you can go faster. Shorter RF pulses allow you to waste less time on that part of the pulse sequence. You can trade signal to noise ratio for speed, and there's number of data points collected at once, which I'll get to. But that's the one that sort of I stuck on, because at that time we were actually collecting only one point of data at once. So the next question, how would you gather multiple data points at once? A, use stronger gradients. B, use shorter RF pulses. C, use lower noise detector coils. Or D, use multiple detector coils. Okay, so go ahead and answer.
There's
All
D's,
right.
D's.
These. All right. So, you've figured me out, of course. It's used multiple detector coils. You can definitely image faster with stronger gradients, shorter pulses, lower noise coils, but all of those are still gathering just one point of data at a time. And so this is what occurred to me in those early days, that actually, if you're gathering signal in different detector coils that are, say, positioned at different places around the body, you can actually get all of that data in simultaneously. Whereas if you're using magnetic field gradients, you have to put one after the other on in a sequential order, which means that if you can supplement gradient encoding with coil encoding, you have a key advantage of parallelism, which leads to speed. So instead of this sequential order, one line after the other, which eventually gets you all the different parts of K-space and the different spatial resolution that you need, you can do this. You can gather multiple lines at once, and of course, scan through the image that much faster. But how would you do this? How do you actually get multiple lines of K-space at once from multiple different detector coils? So think about that for a second. Think how you might do it. If you already know the answer, if you're already an expert in parallel imaging, then forgive me, you can jump right to the answer. But here's what occurred to me at the time. So let's say you have multiple different detector coils, and I've shown them just as squares up at the top here, or rectangles up at the top. Underneath each one, I've shown in white the sensitivity profile. In other words, that coil only sees the part of the body that's basically right underneath it, and then it falls off with distance. Well, what you can do is you can add up the signal from all those coils in such a way that the signal is relatively constant across the image, or you can add them up with different weights and signs such that it actually looks more like an oscillation across the image or two oscillations across the image. And you can do that up to ideally the number of coils that you have. That oscillation across the image is actually, it turns out, exactly what gradients do. They create a modulation of spins, twist them up in sinusoidal variations across the image. So in fact, with this type of combination, we get a different K-space line than with this flat one. And this is just a picture of the back of the envelope. In this case, it was a napkin that I had with me at a restaurant when I was trying to convince myself that you could actually do something like this and you could actually get real additional K-space lines from that. Turns out that you could, which means that you could gather, say, a fifth of the actual gradient lines and then fill in the rest of the lines by combining the signals from different coils in different ways, which means you could image in this schematic example 5 times as fast. You take a fifth of the lines, you only need to switch the gradients a fifth of the time, and then you fill in all the missing lines with those different combinations. And that was a technique called SMASH, simultaneous acquisition of spatial harmonics. There I am again with the SMASH paper back in 1996 and 97. And some of the people that I worked with, Mark Griswold, Peter Jakob, that's Warren Manning, the guy who asked me that fateful question about what I wanted to work on, Bob Edelman. But then there's another perspective as well. And now I'm digging a little more into the MR, but for those of you who know a little or a lot of MR, what happens if you now undersample your signal? So you take a fraction of the K-space lines like I just showed you, say every third line. Well, what happens is the image folds in on itself. It's Nyquist aliasing. And can you unfold that? Can you take that folded image and figure out what really goes where? The Nyquist limit says, no, you can't. But that's only if you have just one detection, one signal. What if you have multiple signals? And this is sort of the so-called sense approach to parallel imaging. The idea is if you have in coil 1 some weighted combination of the different aliased points, the 3 aliased points on the edge, the middle, and the other edge, but if you have a coil whose sensitivity is strongest on one side, then the point on that side is weighted more strongly. Another coil is a different weighting, another coil, and another coil. So you actually have 4 differently weighted copies of that same folded image. And it turns out that if you know what the weightings are, you can unfold it. And I won't bother with the mathematics here, but you can rearrange that into a matrix, you can invert the matrix, and you can get the answer. And this is the technique that was called sense, an alternative approach to the same thing, but once again, you gather less data and you reconstruct it. There's another approach I won't go into detail about, but it's called GRAPPA. This is by Mark Griswold and team. And the idea there is back in SMASH, what we were doing is we were taking, lines from multiple coils and trying to remember, fit them, create these modulations and fit the adjacent lines from that. So go from one point in K-space to an adjacent point. What GRAPPA does is it basically says, wait a second, I don't have to go just in one direction or from one point. I can use all of the measured K-space data around a missing point and find some appropriate combination that gets all of those points together and does a better fit towards what's in the middle. And it turns out, though a lot of people distinguish parallel imaging as happening in the K-space domain or the image domain, there's a way I like to distinguish it better, which is how much of K-space it uses. So SMASH basically involves neighbors in K-space. You do these fits and you combine different coils to move from one point to an adjacent point. In grappa, it's sort of a nice, tight little neighborhood. And in sense, it turns out you can show that you use all of the measured points to fill in every missing point. Okay, so then just the last few slides here. I told you 10 years afterwards, compressed sensing came along. Compressed sensing was interesting because it turns out it allowed you to undersample your data, take fewer K-space points, but then use an appropriate mathematical transform to fill in the whole image without even needing multiple coils. And the way it does it, if you think about it, you take an image. If you want to send that image by email to someone, you send it on your phone, and the phone might ask you, do you want to send it small, medium, or large? And if you want to send it small, it does a JPEG compression. Well, if you're going to compress this image down to a tenth of its size anyway, you could ask, why are we spending all this time gathering all the data in advance? Compressed sensing, developed by Mickey Lustig and others around 2006, is basically a way of pre-compressing the image, of saying, listen, I know I'm not going to need every little piece of the acquired data, so let me gather just a selected set of pieces and use an appropriate transform to generate it. And compressed sensing actually works beautifully with parallel imaging. It allows you to improve parallel imaging, to increase the total acceleration. It allows you to do that continuous comprehensive imaging I was telling you about, that grasp imaging, the continuous radial, for example, that's powered by compressed sensing. And you can also take compressed sensing, and rather than just using a fixed transformation like a JPEG transformation, you can actually learn what the best transformation might be, and that leads directly into deep learning. And so it turns out if you have a whole bunch of undersampled images, and you have a whole bunch of, or undersampled data rather, and a whole bunch of full images, you can train a neural net to convert from the undersampled images to the full image. This is one way to do it, just sort of a simple convolutional neural net. This is the way that our team did it early on, basically sort of by analogy to compressed sensing. I won't go into the details. But basically, you know, this is the kind of technology that I hope you recognize is driving a lot of this vision I shared with you before about the future of imaging. Basically, that you can, in fact, get away with less data. You can get away with different data. You can get away even with different machines, as long as you have the right mathematical transforms to convert that different data into either the images or the answers that you want. So that was sort of my own path, just a few lessons from it, and then I'll finish. The first one is obviously to make room for serendipity. I had absolutely no idea about imaging or MRI when I came into Warren Manning's laboratory, and I'm convinced that that is precisely why I was able to luck into the principles of parallel imaging, because I didn't know any better. I didn't know that, everyone, what everyone else knew, which is that you have to take one point of data at a time. And just a little bit of encouragement for you out in the audience. I mean, I've spent a lot of time talking about the history and the future of seeing. I think one of the key aspects of any discovery and any research is not to be afraid to see things a little bit differently. Okay, so that's a rapid fire, not so Casey case, but I want to thank you all for your attention, and feel free to fire away with any questions you may have.
This is fantastic. Thank you.